Good morning, everyone. I am Raja, Faculty of Mechanical Engineering Department, K.S.Rangasamy College of Technology. Today, I am going to discuss about the air-fuel ratio requirement for IC engine in this videos. So, what is the combustion of fuel? The combustion of fuel is nothing but it is a chemical process in which the fuel react rapidly with oxygen and give off heat. So, this is the diagrammatic representation of combustion of fuels. So, it's needed a fuel and oxygen and the ignition things to start the combustion. So, normally fuel in market we are having petrol, diesel, LPG and CNG as a fuel, and the oxygen we can have it from it air, and the ignitions depend upon the technology what we are using in the engine. Conventionally we are having two things. One is called the spark ignition engine, that is give the ignition. Another is called the compression, the high temperature give the ignition of the combustion process. This is the requirement needed for starting the combustion. After the combustion we will get one is heat. That heat energy is used into take it for a different applications. In vehicles we convert the heat energy into the mechanical energy for running of a vehicle, and we will get a exhaust gases. That exhaust gases what we have it is CO2 and the H2O if it is a completely combustion. So overall the fuel react with the oxygen and started the ignition process by the spark or high temperature compression. We will get carbon dioxide, water and the energy as outcome of the combustion process. So for the combustion process we need air and the fuel. So how much of air and the fuel is required to get that required quantity of the heat for running the IC engine. So we should calculate the air fuel ratio requirement for from the IC engine. So there is a mathematical formula. The mathematical formula tells about the mass of air divided by the mass of fuel. If it is named it as a air fuel ratio, if it is a fuel air ratio, the mass of fuel divided by the mass of air. So based on that we can say it is as a air fuel ratio or fuel air ratio. Shortly we say AF ratio or FA ratio or AFR things. So generally we denote the air fuel ratio as these things: 14.7 is to 1. 14.7 is air mass, 1 is fuel mass. So this is mean that air fuel ratio. So what it represent means the 1 gram of fuel required 14.7 grams of air for completely combustions. So there is no pollutant in the exhaust gases. This ratio is named as a stoichiometric or ideal theoretical air fuel ratios. So you should remember that the 14.7 is to 1 is the stoichiometric air fuel ratio for the petrol. So how we can calculate that 14.7 means for petrol we know that the chemical formula is isooctane C8 and H18, and we needed a oxygen. We get out the combustion output is CO2 and the H2O. For chemically we can balance these equations. We can add the 12.5 and the 8 and the 9. So what we have to do, we have to find out the mass of the fuel and the mass of the air. So we know that what is the mass of single carbon. Single carbon mass is 12 and the single hydrogen mass is 1 and the single oxygen mass is 15, that is around 16. So we can incorporate this mass into that mathematical equations. We will get that the mass of the air is 1904 and the mass of the fuel is 114. The ratio is come around 16.673. So it is come around theoretically, but in practical we have required 14.7 is to 1 as a stoichiometric ratio. Like that we can find that stoichiometric air fuel ratio for different fuel. Another example is also mentioned in this slide, that is called the methane. Methane we needed a 2 oxygen atom for chemically balanced. For a stoichiometric air fuel ratio it's come around to 90. Like that based on the chemical formula of the fuel we have to balance that chemical equations. We can find out the air fuel ratio, stoichiometric air fuel ratio. We represent different fuels and what is this air fuel stoichiometric air fuel ratio for that fuel. Gasoline we know that stoichiometric air fuel ratio is 14.7 is to 1. For diesel we are having a 14.5 is to 1 based on the chemical formulas. And Another thing, we know that the stoichiometric air-fuel ratio is a standard or ideal air-fuel ratios where it is the complete combustion is happened. So we take it as a reference point as that. About the stoichiometric ratio, we can split into two categories. One is called lean mixture, another one is called the rich mixture. Rich mixture is nothing but too much of fuel. Lean mixture is nothing but too much of air. So in the diagrammatic, we can represent the 20:1. The 20:1 is called the lean mixture because it is greater than 14.7 is to 1. So there is a too much of air is there. And the another example is 12 is to 1. It is less than stoichiometric ratio. Here we are having a too much of fuel. So based on our running requirement of the IC engine, we can go for a stoichiometric ratio or rich ratio or it is a lean ratio. In the diagram, we can easily understood where we can use the rich fuel, where we can use the lean fuel from the running condition of the vehicle. So where we can go for a rich fuel, whenever we needed a maximum power, we have to use the rich fuel. That is, in diagrammatically we say 12.6 is to 1. So it is lesser than the stoichiometric air fuel ratio. So it's come around in this band. So it is called the rich mixture where we can get the maximum power. In come around the fuel consumptions, with the economical fuel consumption, we will get one greater than the air fuel ratios, stoichiometric air fuel ratio. That is the 15.4 is to 1. So that is greater than the stoichiometric air fuel ratio, where we can get the very good fuel economy. That means we are having a less consumption of fuel and get better mileage. But the power, you can map this less fuel economy with the power, you can get the average power on that air fuel ratios. But here, when we go that maximum power, we will have that fuel consumption is very low, very high. Okay, fuel consumption is very high, so that we will get a low mileage. Here the power is average, but the fuel consumption is very low and the mileage is very good. So from that graph you can understand that when the vehicle is running at under the average lean conditions, that is under the band of 15.4 is used to under that 14.7, we will get a better mileage. When we run below that condition, we will have a good power, but the mileage has dropped down. So this is the one thing we should know that. Next, the band of range, where the vehicle can do the combustion process and we will get the mechanical energy output. So in this range, the minimum air fuel ratio to the maximum air fuel ratio. We know that the reference point is 14.5. It is called the stoichiometric air fuel ratio. The minimum band is 9 is to 1. So we can go up to 7 is to 1. The combustion process will happen. Below that, there is too rich, so there is unavailability of oxygen is there, so that there is no combustion is happening is there. So for the carbon fuel, the 7 is to 1 is that conventionally running engine, we need a minimum of 7%, 7 mass of air for run the vehicle. Okay. Another thing, 30 is to 1 is the maximum range of the air fuel ratio. That is called, we can go after that. Here we are having a more air and the lesser fuel, so the combustion process is not happening. So that optimum conditions for running of a better running of a vehicle, we can go within this range. 9 is to 1, that is called lean band, and in the rich band. 21 is to 1 on the lean band. So this is called the combustible range for every vehicle, and depend upon the fuel, the manufacturer of a engine can made that range. Within the range, the vehicle is designed there. So this is about the air fuel ratio requirement for the SA engine. On the running condition, we can use the different mode of running during starting and also idling of a vehicle under the normal speed, under the full power condition, under the acceleration. So we on dynamically running condition, we can go for any one of the condition the vehicle is running. So like that, when the vehicle is started, we needed a rich air fuel ratios, and after during the idling condition, we can need also a rich air fuel ratio condition. for normal speed we are not increasing the more throttle. The throttle is average and we will not drastically changing the throttling conditions. On that condition we needed a stoichiometric air fuel ratio where we are having a best economical mode. Here the economical mode is best means we will get a better mileage condition. We are opening a average throttling. But in the starting condition, we are opening a less throttle, but we need a good power to start the vehicle. So we can go for a rich air fuel ratio conditions. And for the power mode, we can have a full throttle conditions. So for the full throttle conditions, we need a high air fuel ratio. That is called a rich air fuel ratio. So that it's come under 12.5 is to 1. This is in this band. So from that things we can understand where are based on depending upon the our running requirement the air fuel ratio is varying. Normally if you want to get the better mileage and better fuel consumptions, so we have to run on the best economical conditions, but that come around the 30 to 60 throttle opening conditions is the best economical conditions we can run the vehicle, and the fuel ratio is maintained on the 15 is to 1, and it is called the normal speed. If you want to go for a high power condition and also on the starting condition we needed a rich fuel. Here the power is maximum but the high fuel consumption the mileage is minimum. So in these things we can understand that we needed a different air fuel ratio requirement for running the IC engine, and also we understood that how to calculate the ideal and the theoretical air fuel ratios for any fuels. So keep learning and growing. So thanks for watching. Thank you very much. Good day.